should make it that much better.
Yeah.
Lili joined us recently from the University of Waterloo, where he did a postdoc. His PhDs are in 2 different subjects from Beijing, and he's taking over the world of language generation. So he has 3 papers, which he's, I guess, are you condensing them in this talk, Lili?
Oh yeah, so the 3 papers are like salami slices. They are following the general framework, but we have 3 different applications. So I'm presenting them as a whole.
Okay, that sounds good. So he's in our department. You can antagonism wherever you can find him. And I will, without further ado, let him make this presentation.
Is this talk being recorded, by the way?
I have no idea. I'm not.
Yeah, so I'm recording it. I left a chat message. So for anyone who didn't see the chat, we are going to be recording the AI seminars from now on, including the question and answer bit. So if you have any problems with your voice being recorded, just send me a message and let me know so we can edit it out of the video. I don't know exactly where we're going to be, what we're going to be doing with the videos yet, but we have a few ideas floating around. So yeah, let me know if anyone has any questions about that. And just a reminder to keep yourself on mute unless you're speaking or asking a question or something, just because we don't want any background noise. So if something is going wonky with anything here, just send me a chat message because I'm going to have it on mute. So just so everyone knows.
And to add to Sabina's point, please indicate your intention to ask a question in the chat, in the text chat, and we will coordinate the Q&A session in the end of the presentation.
Okay, good. Yeah, so on my side, I cannot see any chat. So if someone jumps in for a question, I guess maybe Sabina can talk to me, and I can answer any short questions during the presentation, just mimicking the real presentation in the conference room. Okay.
Sure. Do you want me to bring it up like during your presentation, or do you want to look at questions after, or you don't mind stopping?
I think during the presentation is fine for any quick questions.
Okay.
Okay. Okay, good. Shall I get started?
Yeah, I think you're good.
Okay, good. So thank you everyone for attending the pizza talk. And today I'm going to present search-based unsupervised text generation, which is a group of which is based on several of my recent papers in this direction with different applications. And okay, so this is the pizza remotely delivered to you. Hope you enjoy your lunch at the same time enjoying this talk. So the outline of this talk is, first I'm going to give a brief introduction of natural language generation and also unsupervised text generation. And then we present our general framework of how to do it in an unsupervised way by local searching. And then I will present a few applications, and eventually I will give the conclusion and point out some future work. So, so this is how I learned natural language processing. So just give you a general background of NLP. Maybe 10 years ago when I took some courses in NLP in Peking University, I was told like natural language processing is mainly natural language understanding plus generation. Okay, I feel like it's true because everything can be said in either understanding and then generation. And at that time, I was told like natural language understanding was the main focus of NLP research. And that is also true. If you read the proceedings of NLP conferences, maybe 15 years ago or 10 years ago, most of the papers are about understanding or how to do classification instead of doing generation. And there are a few reasons. One of the reasons was, okay, people believe generation was much easier because you can just generate text by using templates or by using rules. But the problem was, okay, if you generate by rules or templates, they are actually not natural language. It works for like phone call systems. If you book a hotel, like a phone call system, like you type in your, your order ID or whatever, that works. But this is not natural language. And at that moment, if you want to generate very fluent or very flexible natural language, that was not possible due to the lack of powerful machine learning models. And so it actually became possible when we have very powerful neural networks like a recurrent neural network or maybe a sequence-to-sequence framework where you have the training data, you have parallel training data, then you can train a very, very powerful machine learning model. How can I generate a sequence of words which form an output sentence based on some input information? So this only becomes possible after the regime of neural networks. Okay, so actually generating natural language is very interesting from many perspectives. First, from the industrial applications, you know, we have tons of applications like machine translation. Everyone uses Google Translate if you are traveling abroad, or maybe you know, if you are a startup company, maybe there was a very successful startup in China. They are doing headlines. They are doing like news summaries. So you can generate some headlines, for example, for the news, and you can make tons of money. And even for our scientific writing, we sometimes use like Grammarly or like to do grammatical error correction. And you've typed some maybe grammatical incorrect sentences, and it can correct some of the grammar for you. And it's also kind of natural language generation. So, so that's why NLG is interesting from an industrial perspective. It's also interesting from a scientific perspective. For example, if you generate a sentence, a long enough sentence, it's more like an iterative system, and it's kind of a nonlinear iterative system, and it may exhibit some strange nonlinear dynamics for the in the generation process. And also, our sentence may be multimodal distribution, just like given an input, you may have multiple output sentences, and the distribution, the target distribution is not unimodal. It's not only one sentence that matches the input sentence. You can generate many, many sentences. In this case, it's different from multimodal distribution in the continuous case, because all sentences are discrete. And how it affects the machine learning model is still relatively unknown. So I think there are many scientific questions here too. Okay, so as I mentioned, this is the typical, you know, framework of doing text generation in the supervised setting. So the supervised setting means we have the parallel corpus. So we have some data, maybe one sentence or other information like image or whatever. So you have some information as input, and then you have the output. You have the desired output or the ground truth output during training. So you have the parallel data, so that you can make a prediction, like you generate Y1, Y2, Y3 hat, and you make a comparison with the reference, and you can train your model by cross-entropy loss and aggregate it over the sequence. And if you do that, with a very powerful machine learning model like RNN or transformer or very powerful things, you can indeed learn such transformation in many, many tasks. And it's very, very successful. But in this talk, I'm mainly going to tackle the unsupervised text generation problem, which means during training, we don't have the parallel data. So our training set, all the resources we have is just a set of sentences. And we tackle this problem by not even training. We do it by searching. But all the resources we have is just a corpus, okay? It's just a non-parallel corpus or unlabeled corpus, just a bunch of sentences. And unsupervised text generation is also interesting from both the industrial point of view and the scientific point of view. And one example why it could be interesting to industry is, okay, so suppose I'm in a startup and I don't have any resources, or I don't have many people, and I don't have data sets. I don't have data sets accumulated over the years. I'm just a startup. So how can I do text generation, for example, news headline generation? So in this case, I'm doing the no data problem or no data intelligence problem. And definitely machine learning is not a fancy approach. And even with very strong regularization, it definitely doesn't work for generating sentences. It's too complicated for any kind of naive regularization. And also, even if you are in a large company, so suppose you are doing, you are a team leader, or you are you have a team of a few people, and it's impossible to label tons of data samples. That's too expensive, and maybe your supervisor is not happy with spending that much money. So but you still want to do the project. So sometimes you work with the minimum viable project. And in this case, unsupervised approach could be a lifesaver because you can do it. And also, it's also interesting from a scientific point of view, because it's very curious to me, at least, like why we have very powerful language models. We can we have tons of papers like matching the semantic similarity of several papers, or matching evaluating the quality of sentences, like the fluency or whatever. And we also have very good natural language understanding systems. If you do the classification, maybe sometimes it's even better than human classification. But why can't we go beyond the understanding task and make our intelligent system generative? We can communicate with humans by synthesizing new sentences. And also, unsupervised text generation could be a unique problem, which has a different topology than maybe the search problem like AlphaGo or NHS games. There could be unique properties in this problem. So that could be very interesting from the scientific point of view. And hopefully, I have motivated the task. I have motivated the task enough, and hopefully everyone would agree that it could be an interesting problem, and but it's also a challenging problem. Okay, so the next for the next part, I'm going to present the general framework of how we tackle this problem. And if you have any questions, you can also ask for the introductory part. Like if there's anything not very well explained, you can just ask. Okay, if not, then I'm going to go to the general framework. I'm going to present the general framework, how we tackle the unsupervised text generation before we go to detailed applications. So the general idea is we tackle this problem by searching. So if we want to do searching, then we first have the search objective towards which we want to search in the sentence space, and then we obtain a sentence that maximizes the search function, the objective score. And also another component is the search algorithm, because there are many search algorithms, like even like greedy search is a kind of search algorithm. Or maybe you can do sequential search, like you generate the word first and you look for the best next word, and so on and so forth. But in here, we decide to use local search, or even stochastic local search, which means you have a template or you have a prototype of a sentence. And then I do some edit. For example, I can insert a word, I can delete a word, or I can do a bunch of edits as you decide. And then eventually, after a bunch of edits or sequence of edits, I hope the search objective is maximized and it gives you a better sentence. So this is the general idea of what we are doing. And for the search objective, our intuition is that a good sentence in any sentence generation task should satisfy some, some properties. And one of the property is the language fluency. So since we are doing sentence generation, and definitely we want to synthesize a fluent sentence, so we can measure the fluency of my candidate sentence. And this is often approximated by the fluency or the probability predicted by a language model. So the language model is trained to maximize the joint probability of a corpus, of a known corpus. And when the language model is fixed, I can use it to evaluate how likely is my candidate sentence. If it's more likely, then it's more possible that the sentence is fluent, and vice versa. So our first component in the search objective is the language model fluency. And the second component is the semantic coherence or the semantic compliance, because we are generating a sentence in a specific task. We are not generating the sentence for no purpose. So usually we can we have some constraint on the semantic of the candidate sentence. For example, in a paraphrase generation task, we want the output sentence to be semantically equivalent to the input sentence, but maybe the wording or the phrases are different. So the second search objective is to measure the semantic similarity between your sentence and the input sentence. I guess it should be why not here. So it shows like if your, and this is given by some embedding of a sentence given by a neural network. So if the cosine is larger, then it's more likely to be a fluent sentence. If cosine is small, then it's more likely to be a disfluent sentence. And I guess we need to normalize it a little bit before putting it to the scoring function, because we assume the scoring function is positive and cosine gives us -1 to 1. So we need a little bit normalization before putting it to that, but this is a very detailed stuff. The third aspect is some task-specific constraints. Okay. So one example is the paraphrase generation. We want the output sentence to be different from the input sentence in lexicons, in the wordings. Okay. So if I just copy the input sentence, then it's not a paraphrase. So I would penalize how similar in lexicon is your candidate output sentence with respect to the input sentence. So this is a task-specific constraint. And some other example is summarization. So if you want to summarize a short sentence from a long sentence or a paragraph, I don't have a constraint saying you have to use different lexicons. You have to use different words. It's totally fine if you just extract a few words, but for summarization, we usually have a budget of the length. Okay, so if I just put the long sentence as my summary, that's no good. We need to have a short sentence, but convey the main semantics or convey the main meaning of the original sentence. That becomes a summary. So in general, our scoring function is just the product of individual scoring functions. We have the language fluency, we have the semantic compliance, and we have some task-specific constraints. And in this way, we can define the search objective in a heuristic way. And then we need to design the search algorithm. And I mentioned we did it by local stochastic search. And the major reason is first, the output, our output is usually very closely related to the input. For example, if I do the paraphrase generation, then the output sentence is very similar to the input sentence. Maybe a few phrases are changed, a few components are reordered, or maybe I substitute one word with a synonym. So the output is very, it closely resembles to the input, so that we can start from the input sentence and I do some local changes. And the other reason is we sometimes may have hard constraints. For example, summary, my budget is 10. You cannot generate more than 10 words. But if you generate the sentence in a sequential way, then it's very hard to control that you stop at the 10th word. It's possible that at the 10th word, you are still at the beginning of a phrase, then you have to go beyond the constraint. But if I do it by local search, then I can add it at different places of the sentence, different positions of the sentence. And in this way, the hard constraints may be better imposed than sequential search. So that's why we did it by local search, and we did it in a stochastic way. So this is how we did. So this is the general framework of a stochastic local search. So we start from some initial state, which is the initial candidate sentence. And oftentimes it's just the input sentence. We haven't generated anything, we just copied the input. But then we want to generate the sentence like Y star after a bunch of local edits. So we can have a loop until convergence or until your budget is exhausted. So within the loop, for every step, you just find a neighbor, or you just sample a neighbor from the previous candidate. You just sample a neighbor. And then you can either reject or accept your proposal in the neighbor. You can either accept your neighbor as your new candidate sentence, or you can reject that. If you accept it, then your current, the YT, the current candidate sentence is the new proposed sentence. Or if you reject it, then you just keep it as is. You just propose another neighbor and you try another candidate. So depending on the particular algorithm you use, you can you can have different strategies of accepting or rejecting the proposal, and you may have different. You may also design different neighborhood of candidate sentence. So our neighborhood is defined by local edits of word insertion, word deletion, and word replacement. So basically, you can delete a word and you say, okay, if this sentence looks good, or you can insert a word, or you can replace a word. So they are the general edits. But for task-specific edits, you can do some reordering, or if you are doing word selection, you can swap if a word is selected or not. You can swap a selected word with a non-selected word, so that you can satisfy some other task-specific purposes. And in particular, in here, the word insertion and the word replacement is given by the posterior distribution. So, and the reason is because you have, usually the vocabulary is very large, maybe 10,000. If you just randomly pick a word and you try if the sentence is good, usually it's very bad. So that's why we decide to do the word replacement or insertion. When I propose a candidate word, I always propose it by the posterior, so that it becomes a Gibbs step in the Metropolis-Hastings sampling. So it becomes a Gibbs step, and if you follow the Metropolis-Hastings framework, then it ensures the acceptance rate of 1, and it's much more efficient than you just do random propose. Okay, so the first algorithm we had maybe in 2018 in the AAAI conference was the Metropolis-Hastings sampling. It's not really the search algorithm because it doesn't give you the best scored sentence. It gives you an unbiased sample from the distribution you defined. So the Metropolis-Hastings sampling is still, you start from some initial state or initial sentence, and you loop until your budget is exhausted. You sample a neighbor by some proposal distribution, and then you either accept it or reject it by this, this acceptance rate. And eventually you can show that if you loop for many, many times, your candidate Y star, your output is an unbiased sample from the distribution induced by your scoring function. So the exponential of your scoring function then normalize. So it gives you an unbiased sample from the distribution. So when I talked our approach to some of my friends, okay, I received one comment, okay, and the comment was very, insightful. So one of my friends said, okay, in the Metropolis-Hastings sampling, we actually didn't use any property of the stationary distribution, because one of the important property is that after you do the sampling many, many times, eventually you will get an unbiased sample. But in here, we don't mind whether we have an unbiased sample or not. We just want to have a better sentence, or we just want to have a typical sample that I have a higher probability, which means I have a higher scoring function. So he told me, like, you are just using the simulated annealing. Then, of course, yes, we can do it by simulated annealing. So we just revise our approach a little bit, and then we get the simulated annealing. So the major difference between Metropolis-Hastings and simulated annealing is the temperature. So in simulated annealing, you have a temperature like T here. So you start from a high temperature, just means you are less greedy. You can explore different sentences, even if it's worse than your current sentence. And then during the searching process, your temperature is cooled down. So the T becomes smaller and smaller. And then your distribution is peaker and peaker. And eventually, theoretically, you can show it will converge to the global optimum, although the convergence rate is very poor. It's worse than exhaustive search. But the general idea is still that you start from less greedy, and after you have explored your search space reasonably well, you cool down and make your algorithm more and more greedy, and eventually it will give you a more probable sentence, or it will give you a better scored sentence than just sampling from this distribution by Metropolis-Hastings. So this is the simulated annealing search algorithm. And also we can do hill climbing. If we don't bother too much about local optima, then I can just search for the neighbor. And then if someone is better than my current place, then I just move one step and then I search again. So this is just hill climbing. Okay. And I have tried all these approaches in our work, and some performs better than the other. And sometimes the hill climbing just performs equally well than the simulated annealing. And I will discuss a little bit about
Lili,
the
sorry,
reason.
there's a question for you on the chat,
Okay,
if you want
sure.
to have a look.
Sure. So
Thanks.
Can you, so how can I see the chat? Or can you read it out?
Should be at the bar at the bottom. Do you have that?
No, I can't see the Zoom on my side. I can't see Zoom on my side.
Maybe you need to exit full screen
Yeah,
from your presentation.
Full screen.
I can read the question for you if you'd like.
Yeah, you can read it.
It says, how do you choose which edit to apply at each step is the first question.
Very good question. So for every step, we just randomly sample an action. So that's why it's called stochastic search. So every time you search, you may have different result. So I just randomly sample the insertion or replacement or deletion randomly by 1/3 probability. And if I need to propose a word, for example, I insert a word or I replace a word, then the suggested word is sampled from the posterior, so that it's more efficient than a random suggestion of words.
And then you have one more question.
Sure.
In your scoring function, multiplication of 3 scores,
yep.
Why does only the second and third scores get weights and the first score doesn't get a weight?
Okay, very good question. So the major reason is they are multiplicative, so the weights goes to the power. But if you have every of them have the weight, I can have the power weight. I can group the power, together. I can put the power together, and then I just group the. I just optimize the weight without the power. So basically, the weight is the relative weight. And if I maximize the scoring function or I maximize the scoring function to a power of something, they are the same thing. So it's just the relative weight. It's not the absolute power is not very useful.
If I may ask another question about your most recent, about the current slide you're on a moment ago. I'm trying to figure what you go back to the slide you were on. So you started at y sub t. Should that be y sub t minus 1? I'm just trying to.
Very good. Yeah, it should be neighbor of yt minus 1. And then I propose a candidate for this step. And then if it's accepted, then the current candidate is yt, and otherwise it's yt minus 1. Yes,
that's right. I just want to make sure. Thank you.
Sorry for the typo. It will be t minus 1.
I have a question. It's probably easier to speak than type. I tried to type.
Okay, sure.
I really like what you said at the beginning about the science of managing those distributions of words. So then I have a question about how to proceed when your objective, when you think about search, is a heuristic combination of fluency, semantic similarity, and specificity with respect to the domain.
Yep.
So the first thing I think about is the framework is not dissimilar to what we've been working on in the Explainable AI Lab when we talk about generating explanations from some kind of representation. So for the moment, think of an explanation as a generation of a sentence based on a whole bunch of knowledge of existing sentences. For example, you could do a transformation of a frequently asked questions summary to another domain-specific vocabulary. The question I have is, what do we sample and how do we integrate a shift in that portfolio of fluency, semantic similarity, and specificity? How do we know when to adjust those? Because that by itself search through the space, but it doesn't give you evaluation specific to the domain, for example.
Yes, I think the major problem, the major design is still the scoring function and the search actions. And I'm going to present 3 applications. They follow the general framework, but they vary a little bit in the applications. Like they vary a little bit in how we define the scoring function, and hopefully they can shed some light on how to apply it to more
tasks. I like
tasks.
the framework a lot, and I'm thinking like a computational linguist about generating outliers that don't have a high score but make sense. So for example, syntactically incorrect sentences might still be very semantically relevant, and that would mean that a uniform heuristic objective might bias you away from things that would be really useful. Or in the case of the frequently asked questions and explainability, we want to use a vocabulary of who receives the generated text, not a generic vocabulary. So your framework already gives up the control points to do that. So I just wanted to point that out.
So I think in response to your question, maybe we can have some, for example, min or max scoring functions. So if one of the components is not so good, then I just ignore that. But at this moment,
that's okay, because the framework gives you the opportunity to see, which is wonderful. And it might be more subtle. So the literature that you are being successful in is littered with heuristic functions that aren't about, for example, about search. When you talked about simulated annealing, actually don't care. I can't imagine in any world in the future where simulated annealing gives us insight into semantics or fluency. It may accidentally do so. That's why I like your framework, because it applies to give you a control point to add more information about semantic similarity, to be able to deal with fluency, like you could talk about style, satire, all of that. So it's very good.
Okay, thank you. So so I guess I can show some applications under this general framework. And
sorry.
I
have a question. Yes, this is very interesting topic. And currently we are using the neural network to generate the natural language. But I think the most advantage of the neural network is generating the token by token. Seems like very natural. I'm very curious about the semantic score. How to qualify the fluence of the generated English.
Okay, so this is given by the language model fluency, or this is at least what I'm currently exploring is the language model fluency. So this is a third-party language model that predicts the probability of a sentence. So now if I have a candidate sentence with a higher probability, so now I say it's better, it's more fluent. And similarly, the semantic coherence is given by some external scoring function, which has shown very successful performance in different applications. Like I just measured the cosine similarity of 2 embeddings of sentences. Or maybe I can incorporate more like keyword cosine embeddings. They are more like a design, but the general framework, and we can show some examples later that the current approach does work, but they are obviously not the perfect scoring function, but it does work somehow.
Sorry, can you go back to the fluency score function? Yes, maybe it's very detailed. Do you have some paper or do you publish a paper?
Oh yeah, so our papers are accepted, and some of them have already been archived, and some of them are will be on archive very soon. And we will present full details of how to calculate the scoring functions. But they are more like engineering details. And sometimes you change the scoring function. For example, you use the transformer as the language model of fluency. It gives you much better performance. We tried it, but we didn't report it in the paper. But the general sense of our work is not to design which scoring function is the best, but just a new framework. Okay, so
okay, thank you.
Good. So I guess I can move on to the applications, and I will go through the applications briefly and see how I can design the scoring function or the search actions based on the general framework. So the first application is paraphrase generation, and the paraphrase generation is generate another sentence that has a similar meaning, but you have different wordings. And in this case, like the best training institute in somewhere is changed to the best, well, the best digital marketing training institute in somewhere. And it can also be very useful in different NLP applications. So to tackle this problem, we have our search objective as the fluency, which is the language model probability, and semantic preservation, which is the cosine similarity of your sentence embedding and some of the cosine similarity of keyword embeddings. And we have one of the task-specific objective, which is the expression diversity. So I would like to penalize the word overlapping between your candidate sentence and the input sentence. So this is measured by blue, which is the n-gram overlapping score. So if you have a higher overlapping, I say it's the worst candidate. If you have a lower overlapping, I say this is the better candidate from this scoring function alone. But I have other scoring functions. So if you just give me some random words, of course, this scoring function is good, but other scoring functions will give you a low score. So this is the specific search objective in these applications. And the search algorithm is, we use the simulated annealing, and the search space is the entire sentence space with your initial state being the input sentence. And the search neighbor is also the generic object we had for word deletion, insertion, and replacement. And we have one specifically designed operator that is to copy the input word to the output as a candidate of the word replacement. That could save some of the real words that are deleted, then they will never recover. They will never be recovered by going through the posterior, but you just directly copy them and see whether it's better. So these are.
I have a brief comment related to whoever talked about saying it seems natural to generate word by word. I have to disagree. And the reason I disagree is because there's 30 years of literature trying to build abstract representations under natural language understanding, where the formulation of sentences that is compatible with Lili's framework are based on transforming concepts to surface structure. Sorry, I don't generate my words sequentially. I don't think about it that way at all. I think about the concepts I want to relate, think about the relations that I can use and transform into verbs to show what I think, how they're related. And so there's this whole rich literature that informs both the fluency side and the semantic side that is an abstraction of language, topic hierarchies, classifications, relationships, synonyms, antonyms, homonyms. There's a whole rich structure out there. So I want to encourage whoever asked the question to not get trapped into thinking like von Neumann machine, and no one else who thinks that either. Sorry.
Okay. Yeah, this is a very good philosophical discussion, and I mean, we have a full bunch of insights, but cannot be presented in this single seminar talk. But at this moment, we tackle this problem by local edits, and this is the first application, which is paraphrase generation. And the second application is text simplification. Like the example is in 2016 alone, American developers have spent how much money in constructing theme parks, according to some reporters. And then the reference, this is in the data set. The reference is they dropped, the clause, because if you have more and more clauses, the sentence will be more and more complicated. So the sentence simplification task sometimes drop the clause, and they have some reordering of the components. Like in 2016 alone, they put it here, and I don't know why, but the reference is just like this. And they also change constructing to building. So so in here, our key observation is in this task, or at least with the references provided with this task, they sometimes drops the clauses and the phrases, and they also have some reordering structures, and also they have some word substitution. Maybe could be benefit from external dictionaries. So what we actually did was
question, if I may. You give one sentence to one sentence. Did the Seattle-based reporter, did that phrase appear in another sentence later on or earlier? Or
with this example, no. They just dropped the sentence, just dropped the...
So it changed, you're okay changing the meaning as well as just rearranging. Okay, thank you.
For this task, or maybe for this reference, for this data set that is designed for the task. So I'm a pragmatic person, and sometimes I just, I don't define what does it mean by text simplification, but with this data set, okay, if they show that dropping clauses or dropping phrases could be one of the phenomenon that we observe, then now I can design the search operations. Like I can remove some phrase, I can do some word reordering about a phrase reordering in the syntax structure. So in here, we just make use of some parse trees and we do such reordering.
I could easily imagine having two sentences in that place, but as soon as you start opening the door to changing the semantic meaning of a sentence, that, I mean, I could simplify quite a bit by just saying hi.
Well, then you will have a low score for the when compared with the reference.
I see. So you're going to look at some
I'm
way
an
trade-off.
empirical person. I'm an empirical person. I say if the data set shows that dropping clauses or reordering could help, then I can design such operators to make it better.
Okay.
Yeah, that's Russ's example is a good one that says the semantics is conveyed, but it might not score high on some of the other blend of the heuristic objective functions.
Okay, yeah, probably. And so our search objective here also includes some, esoteric scoring function adopted from other papers, which is somehow used in text. This is not summarization. Text simplification tasks, and combining all these scoring functions, we somehow get a better performance than previous tests. And the last application is summarization. And once again, okay, it's more clear that in summarization, we must drop some information. And in this example is, the word biggest, minor, maybe some component, non something, and then the references just drops something like Rio Tinto take over a bit. So in here, our observation is that word in the summary, so this is a reference given in the dataset. The words mostly come from the input, you see? So many of the words just comes from that. And some of the words are changed in its morphology, like dropping changes to drop. But if I just keep the original word, the original morphology, and I even keep the order of these words, it still gives me some meaningful sentences. So that's why for the text summarization, we had a very different search space. And our search space is, we select the word. So we are not generating the sentence from the entire vocabularies, but we just predict a binary indicator for every of the word. So for this word, we predict whether it's selected. For that word, we predict whether it's selected. And some of the words, like the highlighted words, are selected. Some of the other words, they are like 8 words, they are just not selected. So the search space is different. And also we had a hard constraint, like the length of my summary has to be some length, okay? The length has to be 10 words or 12 words, for example, and you cannot exceed the budget. So in this case, I can reduce my search space to exponentially growing to, n choose maybe k. And this reduces the search space to a very, very large extent because the vocabulary size is usually very, very large, like 10,000 or 50,000. But now it's pretty manageable if the sentence is not too long. And since I have a budget of saying the sentence should be exactly 10 words, for example, then my search neighbor is just swap the word, swap the selection of words. Every time I randomly pick a word that is selected, and I pick another word that is not selected, and I just say, okay, this word that has already been selected is now not selected, and that word is now selected. In this case, I can simplify the searching task to a very large extent. In this case, we'll show that hill climbing gives you good enough performance compared with complicated search algorithms. Okay, so these are some of the experiments. I just talked them very briefly in terms of the objective or the search space or the search actions, but they just follow the general framework of unsupervised searching. And so now I'm going to present some empirical results. The first result, I think, the first question, the first research question is how does our model performs in general? And we show some very boring numbers. I just want to skip some of the numbers. And the general conclusion is that our model works much better than all previous unsupervised methods based on, for example, variational autoencoders you sample from the latent space, or based on some other rule-based systems or whatever. Our model performs much better than those previous work in terms of both automatic measures and also human evaluations. And one of my major concerns when we do the discrete search is that whether my generated sentences will be fluent, because whenever I insert a word or delete a word by a single word, it may give you disfluent sentences. But by reading over our samples, it rarely gives you influent sentences. Most of the sentences are still very fluent. So this is a little bit surprising to us. So one of the examples is, this is the paraphrase generation. Where are the best places for spring snowboarding in the US? So the general sentence, where can I find the best places in the US for snowboarding? We still have some large step, like editing in the US, it's changed to different places, but it's relatively rare, but it's very common that we can generate fluent sentences. So this is the main conclusion we have. And the second thing is we want to evaluate whether greedy search is important, is worse than stochastic search, or if it's even worse than I'm just doing sampling, I'm not doing search. So this shows like in the paraphrase generation, this shows if you have the zero temperature, it gives you worse performance, but not too bad. And so if you have the zero temperature, it's just greedy. But if we increase the temperature, we allow the model to explore a little bit, it gives you better performance. And the other thing is we tried no annealing, just means I don't decrease the temperature. In this case, it becomes sampling instead of searching. And if I do sampling, it also gives us worse performance. So the conclusion here is that greedy is probably worse than stochastic search. And also, if you sample, you may be you may be bad at settling down to the optimum, so it still gives you worse performance. But things change a little bit in the summarization task. So in here, I mentioned I reduced the search space to a large extent. So I can now perform some exhaustive search up to the length of 30, okay? 30 choose maybe 8, it's not a too large number. I can run it maybe in a few days or maybe just a few hours. So we can do some exhaustive search experiment. So the result in this, this is the difference between exhaustive search and hill climbing. And the result shows that if we do exhaustive search, it definitely gives you higher scoring function, of course. Exhaustive search gives you the guaranteed global optima. But if you do hill climbing or stochastic search, it's not guaranteed, and usually it's not the global optima. But eventually, when you measure the success of your intelligence system, which is by some established rouge scores or blue scores, it doesn't give you better performance. So this is given by the blue comparison. So this shows in the summarization task, even if I search towards the global optimum, the measure of success of my intelligence system, measured by rouge or other metrics, is similar to what we did by hill climbing. So this is some result in the in the summarization task, but this is not observed in the paraphrase. And we conjecture the main difference is the search space is much more complicated in the greedy. Sorry, the search space is more complicated if you generate from the word space. But if you generate from the word selection binary indicator space, then it's much simplified and greedy is good enough. Okay, so these are some of the empirical results. And I think the major conclusion is, okay, our framework works for a variety of applications, and they generate some fluent sentences, and we have some analysis on the different search algorithm. So I think I can skip this. So I think this is very important, interesting to discuss a little bit about the future work. So so I listed a few directions that can be done following this direction, because it's very new. I don't think many people in the literature, in the community is following our work. I think a few of the future direction is, first, we can better define the search neighborhood. For example, some of our example shows, what would you do if given the power to become invisible? And it's paraphrased to what would you do when you have the power to be invisible? So these are, relatively distinct sentences in the phrase. Like if given, it's changed to when you have. Okay, you change the clause, you change adverbial phrase to a clause, something like that. But currently, our local edits is still, cannot do these things very common. It's still very rare. Large edits are relatively rare because we are doing local search and our neighbor is very small. And when you edit one of few words, the chance of being better is very low. So it's more likely that your proposal will be rejected, even though after more steps or more edits, your sentence could be better, but you are just rejected in the middle. So I think in the future work, we can do better, larger edit steps for a single operator. For example, we can do paraphrase editing, or we can do syntax-based editing. And one of the work I'm currently exploring with some of our master students is combining the discrete sampling with VAE. We just want to put a phrase into VAE and see whether it gives you a diverse phrase, and I put it back so I can do it with different granularity. And also we can do some syntax-based editing. For example, I can swipe around the phrases, or I can generate another phrase, like if A, then B, then I can say B if A, something like that. So these could be some future work from a more linguistic perspective. And the other thing is the initial state of the local search is the real key point of the success of our approach. And our current applications have a huge resemblance between the input and the output. But there are many other tasks that where the input and the output are different. For example, dialogue system, I ask you, where are you going to go? And I can say, I want to go to the grocery shops, or I can play, do some travel. So the input and output could be very different. And also translation, the input is one language and the output is the other language. So in this case, you cannot just put the input as the initial state and do some local changes and say, this is my output. That is highly unlikely. So how can I design an initial state for the general purpose text generation under this framework is also an important research topic. And some of the preliminary thoughts is you can combine the retrieval-based method. You search for nearest neighbor in the training set, and then you take it as your initial state. And then in the output space, you take it as the initial state, and then you do some edits based on the nearest neighbor to be more appropriate, suited to this sample. So I guess this could be another direction. And the other thing is combining search and learning. So this is also the disadvantage of the search-only approach. Our current efficiency is probably a few seconds for one sample. So it's not very efficient compared with learning-based models. But we can somehow search knowledge to a learnable machine so that Okay, who is highlighting my slides? Okay, anyway. Did I highlight it?
Randy posted a question there for you. I'm not sure if you saw it.
Okay, that's very good. So another disadvantage is that our current heuristic-defined objective may be wrong, okay? Because I just define it as I like, but it may not be the best way to design the heuristic function. And it could be noisy. It could be deterministically noisy.
But I like the framework. So for example, knowledge we have about language can be embedded in a structure other than just compiled into the fluency portion of the heuristic objective function. So you provided attachment points to help solve the knowledge acquisition problem. That is the knowledge exploitation problem. When I know about language, I can use it. So I'll carry this on with Lili directly. I have to move to another meeting now. Thanks for all the participants.
Yeah, sure. Thank you. Okay, and we're trying to do a Monte Carlo tree search to combine searching and learning in a very organic way, but there could be other difficulties. For example, we have very large branching factors. And also we have noisy rewards. For example, if you do Go and you say, okay, I win, then of course you win. But now I say, I have a better scores function and the reward is very, very noisy. So how does such noisy rewards play a role in our search and learning for text generation is still relatively unknown. And I think these are the messages I'm presenting for this seminar. Okay. Thank you for your attendance, and you can ask me some quick questions. I have to leave in a few minutes for another meeting, and but I can answer a few quick questions. Okay, I'm done. Sabina?
Oh, hi, Lili. Sorry.
Okay, good.
You got Randy's question he put in the chat before he left?
No, I can't see the chat.
Oh, okay. So he said, how can you exploit knowledge language to focus the fluency search object? Example, having knowledge of concepts, relations, etc. And how to adjust specificity portion of objective to produce listener-reader specific knowledge and vocabulary.
Okay, so we have incorporated some entity information, like I must have my keyword or my entity appear in the target, but we don't have a very strong control on the language fluency or whatever. It's just given by black box machinery, like a neural network. If the neural network says my sentence is fluent, okay, I say good. But we try to decompose the scoring function into a few aspects, and jointly it somehow works. Okay, do you have other questions?
You guys can turn your microphones on if you have questions that you want to ask, if it's easier than the chat.
Hi, Lili. Thanks for the talk. Quite interesting. So when you talk about the summarization task, then you shorten your state space by allowing just a few words to be selected during search. Is that right?
Yes, and also we are not generating from the vocabulary space. I only allow a word that has already appeared in the input in the long sentence to be qualified in my summary. And I don't change the morphology. I don't change the word order, so that my search space is just the combinatorial, like 30 choose 8 is not too scary.
Yeah, no, that makes sense. And have you thought of trying to learn this, like based on the task? Then you try to learn, let's say, the set of words that you're gonna consider during search, or the probability in which you're gonna consider each of the words that you have in your vocabulary.
Oh yeah, so I think it's a very, very important idea of combining search and learning. We can first search and then we do learning, and then we do search again and we do learning. So this is possible. And on the other hand, we may first, for example, do some attention-based, for example, attention-based RNN or whatever, and I induce the selection by the attention weights. And then I say, this is my result, and I do learning, and then I do search, I do learning, I do search. And I can combine the learning and searching in a more organic way, like monoculture search or whatever.
Yeah, no, that's pretty cool. Maybe another idea related to this is you mentioned that when you change a word, then maybe you don't get a good score, and then you won't search in that direction anymore. Maybe one way of trying to tackle this is to learn macro actions, like a set of words that you can change at once. And,
yeah, we have discussed that.
So instead of getting stuck, right, somewhere by just changing a word, then you change a set of words at once. And maybe you have enough data so you can try to learn such macro actions.
Yeah, we have discussed that. And this can be done, for example, by you first search something and you see some large steps, you just enhance your large steps by learning what you call it like macro actions. And then you can put these actions into your action space. I'm not sure I am.
Thanks, Lili. Yeah, thank you.
Thank you. So I think I have to leave at this moment because I have another meeting. And if any one of you have questions, you can send me an email, or we can schedule any like voice or video chat or whatever you like. Is that good?
Thanks, Lili.
Okay, thank you. Okay, bye-bye.
Thanks for coming, everyone.
Yeah, thank you.
Bye, everyone.
Okay, I have to leave this moment. Sorry.
Okay, bye.